So if you have homework questions or anything, I'll answer them next time. Okay, so today we are going to get into calculating internal loads. The idea is that you can calculate internal loads in structures, but to do that, what you need to be able to do is calculate internal loads in inclined beams, beams that aren't horizontal. And the first step to this is rotation matrices. And the idea of a rotation matrix is it allows you to start with a vector expressed in one coordinate system and re-express it in a new coordinate system. Bless you. And so here's how to do it. To express a vector in a new coordinate system, determine the angle, I'll call it theta, about the coordinate system axis, any coordinate system axis, any one of the three, and positive or negative is determined by the right-hand rule. So your thumb would be in the direction of the axis that you're rotating around. That takes the old coordinate system, excuse me, into the new coordinate system. Okay, so for example, well, I'll do the example in a second. And then for rotations about the x-axis, this rotation matrix, we'll call it Q, is 1, 0, 0 for the top row, 0 cosine of theta, sine of theta for the middle row, and then 0 negative sine of theta, cosine of theta. And all of these follow a certain, similar pattern. So now for rotations about the y-axis, this is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And about the z-axis, which is the one we're going to use all the time because we're doing internal loads in 2 dimensions in the xy plane. This rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. Okay, so I want you to notice that X and Z follow like the exact same pattern. You have in the row and column that you're rotating about, you have just ones and just a 1 in the diagonal place and zeros everywhere else. And then you have cosine, sine, negative sine, cosine. Okay, so that's how it is with X and Z. Do you see what I'm talking about? No? That makes no sense at all. Okay, so so we're rotating about the first axis here. So in the first column, in the first row, we have zeros, except for the diagonal place, and then cosine, sine, negative sine, cosine in the remaining ones. And then Y is almost like that, but you know, Y always has to be the difficult one. So we switch where the negative is. Okay. So that's how it is. Y always has to be difficult, but it basically follows the same idea. And then once you have that rotation matrix defined, the vector expressed in the new coordinate system is the rotation matrix times the vector expressed in the old coordinate system. And your calculator will do that. Okay, so let me do an example. So let's say that we have this vector. There's the horizontal, and the vector we want is this with a length of 15. Let's make it a length of 20 so I can do it in my head, because I forgot to bring a calculator. Too late. Okay, so that's 30 degrees, length is 20. In the coordinate system we're used to, this vector, I'll call it U, is 20 times cosine of negative 30, 20 times sine of negative 30, right? So that's 17.32 and 10, negative 10. Are you with me on that? So now express this vector U in the new coordinate system where this angle is 30 degrees. Bless you. And I'm going to show how to do that using rotation matrices. So first of all, notice that this is one you can do in your head because the x-axis of our new coordinate system is just directly along the vector. So what do we expect the components to be in this rotated coordinate system? 20, 0, yep. And so now that angle theta, if we're going from this coordinate system to this coordinate system, what's that angle theta? It's positive or negative 30. Which one is it? It's negative. Counterclockwise is positive. And if you think of it in terms of the right-hand rule, your thumb's in the z direction. And so that's a positive rotation. So theta is negative 30 degrees about the z-axis. So now we just plug negative 30 into that formula for the rotation matrix. So Q is cosine of negative 30, sine of negative 30, 0, negative sine of negative 30, cosine of negative 30, 0, 0, 0, 1. And so you get in decimals 0.866, negative 0.5, 0, positive 0.5, 0.866, 0, 0, 0, 1. So now u, the vector u in the new coordinate system is 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1, multiplied by the vector components in the original coordinate system. So that was 17.32, negative 10, and z is 0. We're working in the xy plane. So you get 0.866 times 17.32. Plus negative 0.5 times negative 10 plus 0 times 0. For the second one, you get 0.5 times 17.32 plus 0.866 times negative 10 plus 0 times 0. And for the third one, you get, 0 times 17.32 plus 0 times negative 10 plus 1 times 0. And that gives you the vector 20, 0, 0. Any questions about that? Instead of telling you how to do this in your calculator up here, since you all have different calculators, go to the text book thing in D2L, and there'll be an appendix that tells you how to do this for your calculator. Okay. It's really quick and easy. Let me know if you have trouble figuring out what you're doing. Okay, so now let's do so now we're going to use this to calculate the internal loads for a beam that's not horizontal. So these are the steps for calculating the internal loads for an inclined beam. And I'm going to use as an example as I go this problem. So we have a beam with a pin and slot joint at the left end. And this slot makes an angle of 10 degrees with the horizontal. And the beam makes an angle of 40 degrees with the horizontal. And the beam has a length of 2 meters and a mass of 50 kilograms. Okay, so step one, calculate the external loads on the beam in the original coordinate system. Okay, so the free body diagram looks like this. We have an unknown force vector up here. I'll call that RB. A pin and slot joint. Has a force with a known direction. I'll call that RA. And then the only other force is the weight force. Since we've already chosen the body to isolate, we can treat that as a point force. So that's 490.5 newtons. And then I'll write out the table. And I'll put the about point up here to calculate this. Doesn't matter where you put it. So my row vector for RB is 0, 0. The force is RBX, RBY. Cross product is 0. Then the weight force. So the row vector is negative 0.766, negative 0.643. The force vector is 0, negative 490.5. and the cross product is positive 375.75. And then last is that force RA. The row vector for that is negative 1.532, negative 1.286. The force vector is 0.174 RA, 0.985 RA. And the cross product is negative 1.2856 RA. I don't know why I kept so many decimal places. And now we have two equations we can solve, and what you get is RA is equal to 292.28 newtons. This one is a scalar, not a vector. That's the one down at the lower left. And then RB is a vector, and it's negative 50.86, positive 202.61. Okay, you've done problems like that a million times. So now step 2. Express every distributed load in vector components in the original coordinate system. So here's what we have after we calculated the external loads. Our free body diagram has the force vector we just calculated at the upper right, so that's negative 50.28, positive 202.61. Down here, we have the force 292.28. And now the distributed load, in this case it's just the weight, is a downward uniform distributed load like this. And what's the magnitude of that distributed load? 490.5 divided by the length. So 490.5, in this case, divided by 2, so 245.25 newtons per meter.
Not integrating over it, it's just simple because there were.
Well, that's just taking the, yeah, it's, I have to think about what you do if that was more complicated.
So,
I- Yeah, just if it's a weight force, you're just dividing by the length and that's all. If it's another thing, then you just have to come up with the function value of it. So if it was a triangle, you'd have to come up with the function for that line. But we're going to be doing it with weights only. Okay, so now if this is the distributed load, then you can think of like our distributed load function or our distributed load vector. Distributed load vector is 0, negative 245.25 newtons per meter. Okay, so we haven't done distributed loads as vectors, but you can, and we're doing it. Okay. Step 3. Determine the counterclockwise rotation that takes the original coordinate system to the new coordinate system, and that what we want from that new coordinate system is the x-axis has to point along the beam. X-axis. Along the beam. There's 2 ways you can make the x-axis go along the beam. You could do it like this, or you could do it like that, you know. Either one of those is fine. They tell the same story, even though the numbers come out different. But I usually do the one that's closest to the coordinate system I'm used to, so I'm going to use this one. Okay, so in this case, we want the counterclockwise angle that goes from this coordinate system to this coordinate system. And what's that angle? 40. So I guess the key thing is to notice that it's positive 40. Okay. Because it's a counterclockwise rotation. If we had to rotate it clockwise, that would be a negative angle. So theta is equal to positive 40. And so our rotation matrix, for all of this stuff, we're going to be rotating about the z-axis. So our rotation matrix is cosine of 40, sine of 40, 0, negative sine of 40, cosine of 40, 0, 0, 0, 1. So now step 4. For each external load or let's say for each external point load, and each distributed load vector re-express in the new coordinate system using Q. So we're just going to multiply each one of those vectors by the rotation matrix we just figured out, and that's going to give us all of these vectors in our new coordinate system. So Q times, Q times that point force there, well, we need to express that as a vector first. And I guess I didn't do that. I didn't write it down. Can someone please multiply 292.28 times cosine and sine of 80 degrees to give me this as a vector? Yeah.
Cosine is 50.
Okay, so, sorry, 50.
0.75.
Okay.
And sine is 287.9.
Okay. And if you multiply it by that Q vector, you get this new thing that is equal to 223.90, 187.87, and then 0 for Z. Okay, so that's in the new coordinate system. That's the force vector coming from the pin and slot joint. Then we have the rotation matrix times negative 50.86, positive 202.61, 0. And that comes out to be 91.27, 187.90, 0. And then we have Q times the distributed load vector, which was just 0, negative 245.25, 0. And you get negative 157.644, negative 187.872, 0.
Is that a cross product, technically?
No, it's a matrix multiplication. You can think of it as a series of dot products. Where did I write this? Up at the top, I guess. So what you're doing is, I mean, the bottom line is like you're making your calculator do it, but what your calculator is doing is taking dot products of each row with that column. And then the position here gives you the column number, and the position here gives you the row number. So this vector here dotted with this gives you the first.
I understand what it is.
Okay.
I'm just writing down the steps.
Yeah.
Like Q times R, RA. Making note.
And I mean, this is another case where, like, if you still had to do this by hand, this would not be a very efficient way to.
Code, like, for the, we did something for the R and something, R. But is there any kind of short codes that I can use on my calculator to put everything in?
Yeah, it depends what kind of calculator. Do you have a TI calculator? Yeah. There should be in the text thing in D2L, there should be an appendix that tells you how to do it. But if there's not, let me know and I'll tell you how to do it. But I think on the 85, you have to go into the matrix thing, edit a matrix. That's how you have to do it, I think. But then once you have matrices, you just use the multiplication sign and it does the matrix multiplication for you. Okay, so here's where we are now. So at the end of this step, we have a coordinate system that's aligned with the beam, which is the same thing as everything being horizontal. And now we can do this internal load thing. So here's what we have. 223.90, 187.87. On the other side, we have 91.27, 187.90. And then we have two components of distributed load. A horizontal one going this way of 157.644. And a vertical one going down of 187.872. And now we have an internal loads calculation. The key thing to notice is that the horizontal part of the distributed load doesn't produce any moment. Okay, so for the moment calculation, we're only dealing with the vertical, but it does produce a force. So how many cuts do we need to do? I'm sorry, I'm sort of racing. I'm just trying to get this done so we can do the quiz. How many cuts do we have to do? There are only 2 points here and here, and so n is 2. That means we only have 1 cut. 1 cut represents the whole thing. N minus 1, yeah. So our cut is for x values all the way from 0 to 2. So the force over on the left is 223.90, 187.87. These are both rectangular distributed loads, which means you multiply by x to get the point force that represents it. So we have a downward force of 187.872 x and a force to the left of 157.644 x. And then the internal loads, T, V, and M. And you know what, I'm gonna stop there. I'll finish this next time and we'll do another example problem. But at this point, it's just going through Newton's laws to calculate those internal loads. Any questions about this right now? Okay, we'll get more practice with that, so I'm not gonna make you do any of these problems yet.